I don't care.
All right, let's have a look at this. So, okay, we're graduating to next level stuff. We got projectile motion here. So, let's quickly go ahead and close everything up. Click everything closed here, just give me 10 minutes. Then I'll let you work.
We'll give you 10 minutes, but I don't know how much work we've done.
Okay, we ready? All right, so we got it. They tell us we've got a 0.357 kilogram stone. It's launched horizontally at a speed of 11.1 meters per second from the top of a 76.9 meter vertical cliff. Okay, we want to know some things. It takes how many seconds? So how long does it take for the stone to reach the ground? The stone lands how far from the base of the cliff? And how fast is the stone moving when it hits the ground? So if we wanted to draw kind of a picture of this, just a representative picture. Physics likes pictures, right? So here's our trajectory, something like that maybe, right? Okay? So it starts off, if we were to draw the initial velocity vector, what's it look like? Okay, pointing sideways, pointing horizontally to the right. Everybody agree? Okay. And the magnitude would be 11.1. Standard units. Okay. All right, so how are we going to do this?
It's a solid pressure across quickly.
Okay, so we're going to take advantage. We talked a little bit about this before. We're going to take advantage of the independence of vertical and horizontal motion here, right? Okay, so we're breaking this into components. The motion's going to be broken into components. We've got a vertical component and a horizontal component, and we can treat those separately, which is great. So the first question then, it takes how many seconds for the stone to reach the ground? Is that a vertical or a horizontal question? It's vertical, completely vertical. It wouldn't make any difference if I were to just drop the stone, or if I shoot it out with a velocity of 11.1, or if I launch it with a velocity of 100 meters per second. It makes no difference, right? The only force acting is gravity, which is vertical, and so all the acceleration is vertical, right? So question number one is completely vertical. Doesn't have anything to do with the horizontal motion. So what do we know about the vertical motion? Let's go back, and all we're going to do here is just treat the vertical motion as a one-dimensional kinematics problem, just like we did last section, right? So what do we know vertically? 76.9. Okay, so the displacement is, okay, you tell me what to fill in. So the displacement, I'm going to call it delta y, because it's vertical, equals
76.9.
almost, there's something wrong.
Negative 76.
Negative. You see why? Yeah. Because the displacement is starting here and ending there, so the displacement's going to be in a negative direction. Okay? Good. What else?
Acceleration.
9.8.
Ah, okay.
Negative 9.8.
So a sub y equals negative 9.80, say. Okay? And what are we trying to find? Well, we know something else. What else do we know vertically?
Initial velocity is 0.
Okay, the y component of the initial velocity is 0, right? This is the initial velocity vector. It has no y component. It's exclusively horizontal, right?
Yes.
So we break it into components. It's a pretty boring entry in the table. We get 11.1 in the x component and 0 in the y component, right? So v naught sub y is 0. What are we trying to find? Time. Okay, so what's the equation we're going to use for that? Which kinematics equation is that going to be?
It's going to be the third one.
No. Oh, yeah, it is. Sorry, third one. Yep, you're right, third one. Okay, so third one is, that's the one where we're going to say displacement equals v naught t plus 1/2 a t squared, right?
Yes.
Okay. So delta y, we can plug in numbers here. Delta y is negative 76.9. Initial velocity is 0. It's going to give us negative 4.9, right? 1/2 times negative 9.8. 4.9 t squared. So that's pretty easy to solve. What do we get? What do we get there if we solve for t? How would we do it? So t squared. There's a glitch. There's a major glitch. Oh, there's all kinds of glitches. I don't know what our programmers were wanting from us here. So we get t squared equals positive 76.9 over 4.9, right? Square root it, and that's about, what?
3.96.
3.96 to two places. Okay, so we'll leave that in our calculator though, right? Okay, so there's a calculator number that rounds to 3.96, so we can fill that guy in. Seconds. Okay? Now, part 2, the stone lands how far from the base of the cliff? That's a horizontal or a vertical question? Horizontal only, right? Because now we know that we can separate vertical and horizontal motion, but the one thing that links both of those together is that it's the same rock, right? So all the events have to happen at the same time. So we know that the time at which the rock hits the ground is 3.96, and you have a better number than that, a calculator number that we can use, right? So then horizontally, what do we know about the motion?
11.1 meters per second.
Okay, so the constant velocity, we can call it average then, right? The average velocity in the x direction is 11.1. We know the time from over here, the time is about 3.96. Calculator number's better. And this is we're trying to find displacement, right? Aren't we? Yeah. So delta x equals what? So which equation do we use? 1. Delta x equals v bar t, and so delta x equals 11.1 times our calculator number, 3.96. What do we get?
43.956.
Say it again.
43.956.
Okay, so to 3 places, so 44.0 meters, rounded to 3 sig figs. And then finally, the stone hits the ground with a speed of what? So what about this part? Now, for this part, we're trying to figure out when this thing hits the ground, this is going to be its velocity vector, right? It's going to have both a horizontal and a vertical component. If I knew what both of the components were of the final velocity, I can just add them up tip to tail using Pythagorean theorem, right? So which one of those do we know? Horizontal. Horizontal stays the same, right? So the horizontal component is 11.1. The vertical component we don't yet know, right? We'd have to add that to our vertical list. How could we find, which equation could we use to find, we'd rather not depend on t, how come?
To derive.
It's a calculated number, right? So we'd rather not rely on t, although we do have a calculator number which is out to a cajillion decimal places, and so it's pretty good derived number, right, calculated number. But there is a way we could easily just use our original information to solve for v final. Number 4, right, the one that doesn't use t. Good, so we could go final speed squared minus initial speed squared equals 2a delta y, right? Okay, and initial speed is 0, so final speed is the square root of all that stuff, right? So 2 times negative 9.80 times, what, do you remember what the displacement was? Oh, there it is, negative 76.9. So notice how the signs work out. Physics gods always make it work out. So we get a positive number under the radical, and what's that work out to be?
38.8.
38 point something. Say it again? 38.8-ish, right? So we end up with a final velocity here. If we add that to our table, run out of room, put it right there, is about 38.8, you said? Okay, but that's a calculator number, right? And we're gonna have to use one calculator number, but at least we didn't have to depend on another calculated number to get that calculated number, right? That's a fresh calculation, okay? So then if we want to find, if this is about roughly 38.8, in our calculator, we're just going to take the hypotenuse of this, right? So V final is going to equal the square root of 11.1 squared plus whatever that calculator number is, squared, right? So about 38.8 squared. So if we use that unrounded number, what do we get for our final velocity?
40.37.
So 40.4 meters per second goes there. What if we wanted to get the angle? Because later on I'm going to ask you for the angle. Yeah, question.
Subtract the amount of seconds from the distance, it becomes that. Like nearly.
Oh, it did accident.
Yeah.
That is weird though. It's just an accident. It's a glitch, another glitch. What are the odds that was going to happen? So what if we wanted to get the angle? How could we get the angle? Okay. Yeah, there's our triangle, right? We could, because later on I will ask you for the angle. If we call that angle theta, right? We can solve for theta by just taking the arc tangent of 11.1 over 38.8, and that would be the angle relative to vertical. Probably we're going to want this other angle relative to horizontal, so we could just subtract that from 90. Right? Make sense?
Yes.
There it is. There's your first projectile motion problem. How do you feel?
Well, amazing.
Amazing, yeah. Okay, you can work.